Hey everyone, today I'm going to give my second presentation on computational chemistry with Q-Chem. This week I'm mostly going to be talking about both finding transition states and determining the energetic barriers for those transition states and for overall reactions. I was going to talk a little bit more about some other stuff. I said that last week, but decided that this was probably going to be enough information, so yeah, this is all I'll talk about today, and next week we'll talk a bit more. So you've probably seen this a lot, many chemical reactions. This one is endothermic, for example. You start from a reactant state, you go through a transition state energy barrier to form your products. The reactant state is going to be a local energy minimum, same with the product state. However, there's going to be a transition state energy barrier that's a saddle point. Um, the local minima for the reactants and products are calculated how I talked about last week, whereas the transition state is calculated a little bit differently due to this nature as a saddle point. And so there will be some other things that need to be done in order to get that state accurately. So in order to find a transition state, you first start out with a constrained state. So you constrain the geometry of your molecules such that you're close to the transition state of the transformation. And this constrained state will be somewhere close to the transition state on the saddle point, but won't necessarily be exactly on the transition state. The point of this constrained state is just to get as close as possible to the transition state, such that the transition state optimization calculation that you perform with Q-Chem is as close to this point as possible. So I'll talk a little bit about how to obtain your constrained geometry after this slide, but for now I'll just talk about how you get the transition state uh, calculation in general. So you start with the constrained geometry optimization calculation. Then following this, you would perform a frequency calculation on your constrained geometry. And while you're performing the constrained frequency calculation, you want to make sure to save the scratch files. This is important because you need to save these scratch files and read them in on the transition state optimization calculation. Otherwise, you won't get accurate results. So I'll show you how to do that. So when you perform the transition state optimization calculation, after you do the geometry optimization, so you start the transition state optimization from the constrained geometry, and you read in the frequency scratch files. So you read in the files by adding this variable to your input file. It's geom opt Hessian equals read. You will also need to, when you're inputting the command into the server, need to specify the directory of the scratch files. So I'll show you how to do that as well. And then once you have your transition state optimization, you'll perform a frequency calculation on your transition state. And one thing that you should note when you're performing a frequency calculation for the transition state is that there should be exactly one imaginary frequency. And this imaginary frequency should be in the region where the reaction is actually occurring. So I'll give you an example of my frequency calculation that has been optimized. So this is a completed transition state optimization and frequency calculation. So this is the transition state of my molecule for water nucleophilic attack of this ruthenium catalyst species. And here you can look at the frequencies and see that there's one imaginary frequency. When you look at the imaginary frequency, it's right where you're expecting the reaction to be occurring. So this water is going to be moving towards this oxyl group to create the oxygen-oxygen bond. And this is exactly where the imaginary frequencies should be. So for whatever calculation you're doing, this imaginary frequency should be in the region where the reaction is occurring. If you get multiple imaginary frequencies or no imaginary frequencies, it means that your calculation didn't go correctly for some reason. So you'll need to review what you did to perform the calculation and try to resolve whatever errors that occurred. So when you're done with this whole process, there should be exactly one imaginary frequency, and it should be in the region of the reaction. So in order to start this process, you'll need a constrained geometry. And there's two ways to optimize a constrained geometry. The first option is probably the easier way, is to look in the literature for a reaction that's very similar to yours and use the geometry that they used for your constrained state optimization. Alternatively, if you're trying to optimize a new reaction that hasn't been done before, you want to scan over a range of geometries and plot the data, energy versus whatever range you're scanning, and find the state that has the highest energy range and use that as your constraint geometry. So I'll talk about that in a little more detail. But first, I'll show you how it would be done if you're using values from literature. So this is a water nucleophilic attack calculation performed by Lin Tong et al. And they found that their transition state geometry had this water and a second water in the active site, where the bond between, or the distance between the oxo-oxygen and the water was 1.715 angstroms. They also had a distance between the hydrogen on this water and the second water at a distance of 1.242 angstroms. And they had the distance between this hydrogen and the oxygen on the carboxylate at a distance of 1.557 angstroms. So using this geometry, I'll try to use my complex and replicate this geometry to get a good initial guess for the constrained state. So I'll go ahead and show you how I did that. So let's get rid of this frequency calculation, and we'll start from the reactant state. Say you optimize the reactant state. It should be mostly pretty straightforward after watching my previous video. But you'll need to modify it, of course, such that the geometry matches what's given in the literature. So the first thing I would do here is rotate these water molecules so that it's in the orientation that's given in the literature. So I'll want to rotate this water molecule. And put it sort of in the right position. And then rotate this other molecule. That looks about right. We have these hydrogens pointing away so that these oxygens can face towards each other. We have this hydrogen facing towards this oxygen, and this hydrogen facing towards the sulfonate. In the literature, it's actually a carboxylate group that they hydrogen bond towards, but I found by comparison that this is actually a more, it's a lower energy state, but the difference in geometry will be close enough to the transition state that it doesn't really matter. So now we want to constrain our geometry so that the distances that are given in the literature are the same as what we're constraining for our constrained geometry optimization. So the first thing I'll do is constrain this water oxygen and the oxo oxygen. And so we'll do that by selecting the appropriate atoms and going to build, set geometric constraint, and we'll want to change this to constrain and set the distance of 1.77151 angstrom. Okay, so when you do this constraint, when you set this constraint, you'll see this little thing pop up that shows the distance between the two atoms. If it's green, it means that the distance is what you constrained it to be. You'll see as we change the geometry that it can go red, which means that the initial geometry that your molecule is in is not actually set to the constraint that you set. So we'll mess around with this a little bit and we can see how this changes as we change the other geometries. So the next thing I'll want to change is the distance between this hydrogen and this oxygen. And we'll do the same thing. We'll go to build, set geometric constraint, change it to constrain, and set it to a distance of 1.557 angstrom. And apply. And as you can see, this other water molecule moved to set this constraint, and so it's now red, and it's no longer in the correct geometry. But we can go back and forth and set these such that it gets closer and closer to the correct geometry, and eventually all three of these distances will be the correct distance. So next I'll set the distance between this hydrogen and this oxygen, which should be a distance of 1.242 angstroms. And now this geometry is correct, this distance, but the other two are now incorrect. So we'll want to modify these, continue setting these constraints until they're all the correct distance. So one thing I notice here is that the angle is a little wrong once these move together. So what we can do is rotate this a little bit so that it gets closer to the correct angle. And we'll just keep setting these constraints until all of them are correct. So I'm going to reset this constraint to be 1.557 angstroms. Reset this constraint to be 1.242 angstroms. And now reset this one to 1.715 angstroms. And as you can see, these distances are getting a little closer with each time we set this constraint. So now we have two of the bond distances that are correct. We just need to continue doing this process until all three of them are correct. And there we go. Perfect. We now have this geometry correct. The OO bond distance should be 1.715 angstroms. And if we look at that, it is 1.715. And if we look at this distance between the hydrogen and the oxygen of the two waters, should be 1.242 angstroms. And it is. And this last one between the hydrogen of the water and the oxygen of the sulfonate should be 1.557 angstroms, and it is. Okay, so now that we have these constraints, we'll need to set this geometry in the input file of the constrained geometry optimization calculation. So if we look at the input file given in the GUI for Q-Chem by going to calculation, Q-Chem setup, we can scroll down and we see this new section, opt constraint, in the input file. So when we do the geometry optimization, we'll need to add this into our file and copy in the new geometry. So say we already had the reactant calculation finished, we can just copy in those parameters and paste in our new geometry and constraint to these parameters. So here I have my optimized reactant that works successfully. We could just copy this, or we don't even need to copy it. We can go straight from the input file. Don't worry too much about the variables because this is just the parameters that I use for my calculation. But we can go into Q-Chem, and it should be ruthenium 5. So between the oxo and the two negatively charged ions, it should be a +1. So we'll change this to +1. And should be a doublet. So we have that correct here. We have a +1 charge in a doublet spin state. We can copy in our geometry. Paste it in. And we also want to make sure to copy in our constraints. So we'll copy in this constraint section and paste it in just underneath the variables. It doesn't actually have to be just underneath, but somewhere in your input file should be this constraint section. So we have all of our optimization parameters set up. Should be optimization still. You don't have to change anything about that. Just make sure you have this constraints section and your new geometry. So we'll save this as a new file. We'll save it as WNA for water nucleophilic attack constrained opt. And that should be suitable constrained geometry for our calculation. So we can save that as our input. And from there, we would just send it to the server and run it exactly how we would have done the way I showed in the last video. So you just send it to the server, run it using Q-Chem, specify the number of processors, and then the input and output file. So it's exactly the same as running a normal input. You just have the constrained geometry. If you don't know the correct geometry, say you're performing a computation on a reaction that's never been performed in literature before, you would need to perform a geometry optimization over a range of distances. So for this example, this is from the literature. They have a reaction called intramolecular two-metal radical coupling. So in this reaction, two catalyst species come together and this OO bond distance gets closer and closer together. So what they did is performed a geometry optimization at a range of distances for this OO bond distance. It would be exactly the same as I showed for making this constrained state, except it's a lot simpler. They only need to specify one distance, the distance between this oxyl oxygen and the distance between another oxyl oxygen. And they would perform a geometry optimization with those constrained states over a range of distances. And once they do that, they should have electronic energy values for each of those distances, and they plot that as the distance changes. So here, the red and the blue is just the difference between a low spin and high spin variety. They found that the low spin is actually the correct, the lower energy gap. So from this data that they get, they find that the highest energy point is when the OO bond distance is 2.05 angstroms. So at this distance, at this constrained geometry that they calculated with the distance of 2.05 angstroms, this is what you would then use for the transition state optimization calculation. So following the geometry optimization, you'll need to perform a frequency calculation on your constrained geometry. So I'm just going to modify this file we just made. Imagine this is your constrained geometry. Imagine you perform the geometry optimization with the constraints, and this is the output you got. You would use this geometry. Obviously, you would change job type to frequency, and you would you can delete this constrained section. You don't need that for the frequency because the geometry is not going to change. So you would then send this to the server. I'll go ahead and save this as a frequency. Exactly the same, just changing the name so we can see what's going on here. We now have our constrained state, and we're performing a frequency calculation. One thing I mentioned is that we need to save the scratch files so that they can be read in for the transition state calculation. I'll show you how to do that now. We'll send this file over to the server. So I'm on my server here. So we'll make the directory DFT test, just like we did last time. And then we'll navigate to this folder by using cd DFT test. And there's nothing here, so we'll need to send over our file. So in this folder here, I have the file, so we'll send it over with using SCP. SCP WNA constrained frequency.in, and we'll send it to our server. In the directory we just specified. And it should send over. And now when we look at this folder, it should be, the file should be here. Okay, so we have our input file. Now we want to make sure to save the scratch file so that they can be used for the transition state calculation. So we'll do the same thing we did last time. Q-Chem NT4. This is probably going to take longer than a normal geometry optimization, so might want to up the number of threads you're using. Let's say 8. Should be fine for this calculation. It should be done in about a week or a few days to a week. We would then want to add the flag -save. So this is the important part. You need to add the flag -save to save the scratch files so that they can be read in for the transition state optimization calculation. And remember, this is only for the frequency calculation that you're performing on the constrained geometry. So we're performing this frequency calculation. We add the flag -save. We specify the input file, specify the output file, and run and it should run correctly, and the file should be saved. So let's go ahead and test it out. Let's run it. We'll ls to look at the files. We'll tail the output file and see that it's running. So you would let this run and get your frequency calculation finished. Frequency calculations for these larger molecules tend to take a bit longer, so may have to wait longer. But you would just wait for it to finish, and then once it's finished, you'll perform the transition state optimization calculation. So I'm just going to go ahead and kill this process because we don't need to run it by using kill 2772298. But let's say we had, okay, so we did our frequency calculation and the scratch files should be in the scratch directory. On this server, the scratch directory is in /data/scratch. Help if I could spell it right. It should be fine. /data/scratch. We need to make sure to CD into it. And we can see the scratch directory for all the calculations that have been run on the server. So it looks like the scratch directory wasn't saved for this calculation, probably because I didn't have it running long enough, but your scratch files will be saved. So you know your scratch files are in the directory /data/scratch. It's probably different on whatever server you're using. But you would need to call that in when you're doing the transition state frequency or transition state optimization calculation. So I have an example of the transition state optimization input file. So you'll have your constraint state geometry that you've already optimized, and that should be at the top of the input file. You would make sure to change the job type to TS. So that's indicating you're performing a transition state calculation. This is a transition state geometry optimization calculation that's attempting to find the saddle point. So you change your job type to TS. I would also change the number of cycles to a much larger number because this can take a large number of cycles before you find the correct saddle point. So 8,000's a bit excessive. You probably want to use maybe 1,000, maybe 500, something like that. But you add this geom opt max cycles, enough to find the transition state. And one other important thing you need to add is this variable geom opt Hessian equals read. So this is saying the calculation should look for the scratch files to perform the transition state calculation. And it can only do this from a frequency calculation. So you're telling Q-Chem to look for the scratch files for the Hessian. And in order to indicate where the Hessian is located, you need to add another flag to your input. So I'm just going to send this file over to the server, and then we'll try to run it using while specifying the scratch directory. So I'll do the same thing, scpn the transition state optimization file to the server. Into the directory that we were just using, just to make it easy. And it should send over. Now if we ls, we should see our transition state optimization input file. We have this. We can just take a look at it using Vim. And things look correct. We got the right geometry. We've got the transition state job type. We have geom opt Hessian equals read. So the input file should be all set up. The way we would run this is the same way we did before, but adding one additional item. So I'm just going to go ahead and exit Vim. And we have all of our scratch files here, so we can easily locate them. So we'll set it up using Q-Chem NT8, specify the number of threads like normal. We set up our input file. set up the output file, and then we write the scratch directory. So here I would put /data /scratch / the folder where the scratch files are. So for this one, it doesn't really matter. I'll use this scratch directory. I actually think it's the right one. So we add that to the directory and then make sure to put and so that you can run the calculation in the background. And this should be good to run. And now you're telling Q-Chem to run with 8 threads with this input file. I'm writing to this output file and using this scratch directory. So it'll read the Hessian from this scratch directory. This is very necessary for transition state optimization calculations, because otherwise the frequencies that you get following the calculation after this won't be correct. You'll get multiple imaginary frequencies, and it won't be true to the quantum calculation. So just for an example, I'll let it run, make sure there's no errors. And I need to be in the folder. And it looks like it's running okay. We'll press enter to get back into the terminal. ls to look at the files, and we'll tail our output file. And it's running. So now we have our transition state optimization calculation running with the Hessian read in from the scratch directory, and this will eventually give us the transition state geometry. The transition state geometry that corresponds to the saddle point of the transition. So once we have this geometry, it's a simple frequency calculation. You do it exactly the same as you would do any other frequency calculation. Let me just kill this job real quick. And you'll have the transition state geometry, and then you'll do the frequency calculation. Frequency calculation, as I said, exactly the same as before. I'll show an example of my input file. Oh, so I don't have an example of the input file, but it's exactly the same as any other frequency calculation. You use the geometry given to you by the transition state optimization, and then you change the job type to frequency. There's nothing different than a regular transition state frequency calculation. So if you do that correctly, you should be able to find this energy corresponding to the transition state. And from there, by using a relative calculation, you can determine the activation energy for whatever calculation you're reacting or you're calculating. So performing the reactants and product calculations is exactly the same as you do any other calculation. Transition state, you would find how I just talked about. So you should be able to find this exact energy graph based on your calculations. So just as a reminder, you have these 4 steps you take. You get the constrained geometry, perform a frequency calculation on that constrained geometry, saving the scratch files. You then perform a transition state optimization calculation, reading in the scratch files from your frequency calculation. And then you perform a frequency calculation on your transition state optimized geometry. So from there, you should have your transition state geometry and energy value. So say you have frequency calculation for reactant state, transition state, and product state. You want to know the energy barrier, the activation energy, and the change in energy between the reactants and products. These are both useful pieces of information. One thing to note is that if you are studying a complex reaction where there's many steps, and you don't know what the rate determining step is by some experimental evidence, you would have to perform this on every step of the reaction to determine the one that's the lowest in energy, or the highest in energy, rather. If you know what the rate determining step is experimentally, that makes things a lot easier. You only need to do this on one transition state. But yeah, if there's multiple steps in the mechanism, you would just you would do this for each step in the mechanism and determine the step that requires the most energy, and then that would be your theoretical rate determining step. So now we want to find the energy of those transitions. We have our geometry and frequency calculation for the reactant product state. If we wanted to, we could perform a single point energy using a high level of theory on both of those states. And we want to perform, and we know our transition state with the frequency. And you could do the same single point energy with a higher level of theory for the transition state as well, so that you have consistent data for all three states. You would then calculate the energy barrier between the reactant and the transition state, and the reactant and the product state to find the delta E and the activation energy. And you can do that using this equation, where delta E is equal to the delta E for electronic energy plus the delta H minus the delta S times the temperature. And as we stated last time, temperature is going to be standard unless you change it, and it should be 298.15 Kelvin. One thing that I should note is that this calculation should be done entirely in one type of unit. What's typically done is kcals per mole. It's probably the most understandable to most chemists. So when you get your electronic energy, just make sure to convert that to kcals per mole using this conversion factor of 627.509. I did do this for one of my complexes for water nucleophilic attack, the reaction we've been looking at, and found that I have an activation energy of 15.8 kcals per mole. And I'll quickly run through how I was able to determine this value. So what you'll probably want to do is do this in an Excel graph or an Excel sheet. Here I have places for the electronic energy that gets converted to kcals per mole by the conversion factor 627.509, like I stated before. I have a place for the enthalpy, which should be given in kcals per mole. And then I have a place for the entropy, which is given in calories per mole and then gets converted to kcals per mole by division of 1,000. So then we find our energy value by adding the electronic energy, the enthalpy, and the entropy multiplied by temperature, having each of those components in the unit of kcals per mole. It's pretty straightforward, just like you would see for most thermodynamics calculations. So let's just go ahead and do that. We'll first look at our reactant state. We'll open up the reactant frequency calculation. All of the information should be in this output file. So if we Control F to look for total energy, it gives us total energy in the final basis set. Obviously, if you do a single point energy calculation, you would take the data from there. You don't take it from the frequency calculation. But for this purpose, we'll just take this electronic energy, paste it into our Excel table for electronic energy. In Hartrees, it gets converted to this value in kcals per mole. We would then go back to the output file, scroll to the bottom to find the enthalpy, and paste this in. Notice it's in kcals per mole. and then also get the entropy. Notice this is in calories per mole, so it needs to be converted to kcals per mole, which I've already had set up in this Excel sheet. So now the total energy for this molecule should be negative 1,430,000 kcals per mole. And remember, this value is only significant when it's relative to something else. So it doesn't really make sense now, but once we paste in our other values, it'll make a lot more sense. I also have this relative energy section by just subtracting the total energy from the total energy of this initial state. So this is the total energy minus itself, because this is what we're making everything relative to. This relative energy is also subtracting from the total energy of our reactant state, and the product is also subtracting from the total energy of our reactant state, just so that we're all relative to a single point. We could then look at our transition state frequency calculation. I already showed this a bit. Remember, it had the imaginary frequency in the active site, and that was the only imaginary frequency, which is very important. We'll go ahead and open up the output file, which is this one here. Again, we'll search for total energy. We'll copy it from the output file and paste it into our Excel sheet. And then we'll also copy and paste the enthalpy and entropy. And we'll do the same thing for our reactant state. Look at our our product state rather. Look at our frequency calculation for the product state. Search for the total energy. Paste that into our Excel sheet. And then also paste in the enthalpy and entropy. So we can see now that all of these values are relative to our reactant state, these energy values are much more, they make a lot more sense. So the energy to go from the reactant state to the transition state, meaning the activation energy for this step of the reaction, is 15.8 kcals per mole. The delta E between the reactants and products is going to be 11.95 kcals per mole. These are pretty realistic values, and they wouldn't get values around this amount wouldn't surprise us at all. If you start getting crazy values like 200 plus kcals per mole, you're probably something went wrong in your calculation, or you're not calculating the difference between the correct states. Say you forgot an atom in one state, or you're not accounting for some atom, or the transition is not a realistic transition. That's totally possible too. Could be undergoing some other path that's much more optimized energetically. So we now have our energy graph. The way I made this graph here is just making arbitrary points 1 through 6 on my x-axis, allocating those to the different states in the geometry, and then having those values relative to the energy that I calculated. So obviously, when the reactant state is going to be 0, the transition state is going to be equal to this relative energy for the transition state, and this energy value is going to be equal to the relative energy for the product state. So we got a pretty nice looking energy graph, This probably isn't a flat line to this harsh angle to a flat line. It's probably some curved line like this, but this is very good representation for what the reaction is going through. This is going to be the highest energy state. This is the reactant state. This is the product state, and they have a reasonable energetic barrier for the reaction transition, giving us an endothermic reaction. So that should be everything that I wanted to cover in this this meeting. We talked about how chemical transformations occur using a transition state energy barrier through a saddle point. We talked about how to find the transition state using 4 steps. We talked about how to find a constrained state, either using values from the literature and building the molecule in IQmol, or by optimizing a range of geometries in the reaction coordinate and finding the highest energy point. And we talked about how to use the energies that we obtained to find a reaction coordinate for a specified reaction. With that, give me any questions if you have them. I'd love to hear how things work out for you. And if they don't work out, I'd be happy to answer any questions. So yeah, thanks for listening, and see you all next time.